Hey, so it's Ben Holcomb, just giving a quick video tutorial on how to use SolidWorks for finite element analysis simulations, specifically with respect to determining the eigenfrequencies or the natural frequencies of a simple structure, such that we can compare those to what we might have been able to obtain from an experiment. So I'm sharing my screen here. I'm using the UTS WorkSpace to access SolidWorks, which is one of my favorites, along with some others. As you can see here at the start, I've already opened SolidWorks. I have done a little bit of a rehearsal of this, so hopefully it goes quite well. There are some warning messages I get when I create a new part because of apparently some lack of templates that are available. This is just a very simple structure, a rectangular plexiglass plate. We can quickly draw that up in SolidWorks as a solid block of material. The dimensions for the plexiglass plate that have been given are 530 millimeters wide by 320 millimeters deep, and that's the extent of what we need. If we exit the sketch, we can then define the depth, which is 23 millimeters thick. Okay, so some of the materials or the plates that exist that there may be some data sets available for in the SimCenter test lab modal analysis training material might have a slightly different thickness. 23 millimeters is a bit of a strange thickness. So often you could get a 25 or a 25.4 millimeter thick plexiglass. It may be that those thicknesses have been used instead of 23, but 23 is the dimension I've been provided with by Siemens in respect of the model that they've made available as tutorial material in their GTEC solution. So we have now our component. We can go to simulation and we can start a new study. It's a frequency-based study. There are some static solutions as well that we can access, but this is going to study the resonant frequencies and mode shapes of these kinds of structures. And this is a typical scenario that we might be involved with as a practicing engineer, making components, brackets, plates, other sorts of simple structures. We need to understand often what the natural frequencies of those structures are. So the first thing I need to do is obviously to apply a material, and we have a large list of materials available within SolidWorks. This is an acrylic material, a clear acrylic material, otherwise known as plexiglass. So I apply a material. The material properties include, of course, the density, the Young's modulus, the Poisson's ratio, and so on, that would be important if we were doing a static stress analysis. They, of course, are important, and the density as well are what determines the frequencies of the natural frequencies for this material, for this sample, for this component. Once we've applied material, we can define some of these other properties here, but because this is a free analysis, there are no boundary conditions, there are no fixed loads, we don't have any other components, so there are no connections. We can determine the study properties. The number of frequencies, particularly, we should always, for a free analysis, ask for more than 5 natural frequencies. I believe there's a limit of 10 for this education version of SolidWorks simulation. So I would ideally like to have a few more than 10. It would also sometimes be nice, as we do with experiments, to be able to define the upper bound, say up to 1000 hertz or up to 2 kilohertz, for example, something like this. But that will require the use of a different iterative solver. So if we check this one and say a kilohertz, try to OK this, it gives us a warning that we need to use a different solver. So we'll just keep it simple for the sake of this demonstration. I'll ask for 12 frequencies. I think it will only give me 10 in the result. And there are some of the properties here that we might be interested to include, but again, for the sake of a simple demonstration, we'll ignore those or leave them as the default. I can then Separately to running the study, I can create the mesh as a first step, because often if it's a more complex structure than the one that we have, we might want to do some mesh refinement. We may also want to specify the element type that's been applied to the solution. So there are some options to define the element type. We can change the mesh density. We can check the mesh quality. And so sometimes, or I would recommend that we always build the mesh in separate steps. I think ideally we would have more than one element through the thickness. So that will require that we have a slightly finer mesh density. And we can either use the slider here, or we can specify here, say the element width. Of course, the more elements we have, the longer the solution takes. It may be that we get a better result. At some point, the result accuracy will plateau, and extra elements don't really help us any longer. It just makes the job take longer. So we run a convergence check, and we do a mesh sensitivity analysis, typically when we rely on finite element results for real. Let's have a mesh density of around 10. It's now building the mesh. And as you can see, we've got 2 elements across the thickness. Remember, the thickness is 23. So we've got a significant number of more elements. We're looking to make sure that we don't have any very high aspect ratios of these elements. This is a very simple structure. So these elements are all very nicely regularly shaped. They're tetrahedral elements, which are the easiest types of elements to build a mesh from. Quadrilateral elements are more challenging, hexahedral elements. But again, for the sake of a simple analysis of a simple structure, these elements will be perfectly acceptable. We can then run the analysis, and it's going to take a while to complete. You can see the timer here, or the activity monitor here, as it runs through the solver. We could also model this type of structure analytically. There are analytical solutions for this type of plate-like structure and for cantilever beams and so on. It has given us 12 frequencies, so that's nice. You might notice that there's no mode shape for the first natural frequency. Or I should say there's no mode shape. There's no flexible mode. It's actually a rigid body mode. You can see the original position here was of the, I should be able to probably turn on the undeformed model. It will be available in the settings, but the deformed shape is this, where the blue one is. The undeformed shape is what I'm kind of highlighting here as I scroll over it. So that's just a rigid body mode in the X direction, the first natural frequency, and it's at 0 hertz because it's free. Similarly, there's a rigid body mode in the Y direction, a rigid body mode in the Z direction, and as you can see, and there'll be 3 rotations. One about X, one about Y, one about Z. So those 6 rigid body modes we typically can ignore. They're all at 0 hertz. We're not interested in rigid body modes. They do exist, and they're important in some cases, but it's the flexible modes that we're interested in. So we really start to see modes of interest from mode 7 after the 6 rigid body modes. And the first flexural mode is displayed here, is animated here. It's a torsional mode. We've got a frequency, a natural frequency of 131.7 hertz for that mode. We can scroll through these. So that's the first bending mode in the long direction, I would say. Of course, it's less stiff in the long direction than it is in the short direction. So that's our second natural frequency at 132.83. Those are very close natural frequencies, as you'll notice, and that's why this particular plate is used as a demonstration for the software, Siemens SimCenter Test Lab model analysis software, because it's really nice to be able to separate those 2 frequencies apart from one another. You need a fine frequency resolution to be able to do that. And so that's part of the point of the exercise, is to be able to compare and contrast those 2 relatively close bending and torsional modes. This 9th or 3rd flexural mode is what I would call a second torsional mode. So you can see these adjacent corners are out of phase with respect to one another in terms of the motion. And there's like a nodal line running here and through the center. There's the second bending in the longitudinal direction. And at some point, hopefully we'll see first bending in the short direction. And then the 12th mode is another kind of combination of bending and torsion. It should be possible to animate these results. We can, of course, list the resonant frequencies in a table if we want to compare and contrast those, which might be useful. In the plot tools, we can do some section clipping. As I said, we can animate, which is quite nice. We can change the number of, we can reduce the speed. We can pause. We can export as an AVI. Maybe go back to some of the earlier frequencies. Have a look at those. We can choose where we want to save that one. That completes this tutorial exercise. I hope you found that useful. See you soon.